So our next speaker is Monika Schleier-Smith from Stanford University, and the stage is yours. So.
Well, thank you for the invitation to be here. I'll be talking today about graph states of atomic ensembles entangled by light. And to give some motivation in the framework of this conference, I thought I'd start by sort of touching on what are kind of two different routes one might take to explore topological physics in kind of, what I would call engineered quantum systems we can build in the lab. And these are, you've sort of heard about these already in the past couple of days. One is that you might have some programmable kind of hopping, let's say in some lattice, that you can use to engineer a gauge field and make your, let's say, cold atoms act like they're seeing an effective magnetic field, and that could be a route to studying quantum Hall-like physics in this engineered system. And another approach is actually to explore things like, let's say, toric code states, where one route to making them is actually starting from a very versatile resource state called a cluster state or a graph state, and then performing measurements that can steer that state into a topological one, and that's something you've heard about, for example, in Adam's talk. And many of the systems we play with in the lab are confined to sort of doing local things on a lattice. But what I want to talk about today is kind of a toolbox for being able to go beyond that and to have actually control of non-local couplings, which we hope might open some new opportunities that could range from sort of engineering topological flat bands, exploring topology in higher numbers of spatial dimensions than we have accessible in our universe, or in completely non-local settings. And also being able to have control over, for example, do we have periodic boundary conditions? Is our system living on some topologically non-trivial manifold? All of these are directions one can hope to go with flexible control of non-local interactions. And the way that we achieve that in our lab is by coupling cold atoms to light in an optical cavity. And so I'll be talking about this as a toolbox for both sort of programming the interactions between sites of an atomic array. In our case, it's an array of atom clouds. That can be a route to then engineering kind of the hopping of the spin excitations. And then another sort of related direction I'll talk about is how one can actually really probe and control the structure of entanglement between the nodes in this array. And I'm actually going to start by this direction on the right, engineered entanglement, and then sort of move into this broader picture of programmable interactions. So the sort of building block is going to be that we have the system where essentially photons can let distant atoms talk to each other. And the fact that one has these photon-mediated interactions allows us to take advantage of the high degree of control we have over light to start to program the structure of those interactions. And we'll also be adding in not only the ability to sort of control how we drive this cavity, but also to sort of take pictures of what's going on inside and use that to probe spatial correlations that entangle. But sort of just to start with the basics of how do spins interact via a cavity. The picture you can have in mind at sort of a cartoon level, if I just have two atoms with two spin states each, is that I can have an atom flip its spin, emit a photon into the cavity, which gets absorbed by another atom that flips its spin, and that can be the basic building block for these photon-mediated interactions, or equivalently, photon-mediated popping of spin excitations. And just to sort of, that was with two atoms, and just to say that none of this is happening in a vacuum, there's a whole wealth of research that's being done leveraging these photon-mediated interactions, either to engineer, for example, in the setting now of not two, but of many atoms, to engineer entangled states where, for example, the quantum fluctuations in the spins are squeezed for enhancements in metrology, or using these sort of non-local atom-photon interactions to generate a number of models of interesting for quantum simulation. And as one example, you heard a little bit yesterday about topological photonics from John. So all of this is sort of, there's a wealth of research, both more in quantum control and quantum many-body physics. And I would say the main thing that we've kind of been adding to this toolbox is typically one often works in a regime where the way that one probes the system is via the light that's coming out of the cavity. And there's, in fact, a lot of information you can get by just looking at this light and learning primarily then about sort of collective observables. But much of our focus has been on actually trying to kind of minimize the information in the light that's leaking out, and try to get, to the extent possible, coherent dynamics of the spins inside mediated by the light field. And so then rather than detecting by the light leaking out, what we'd like to do is actually detect by imaging, and that's a direction that I would say the field has been pushing in our group, Dan Stanford Kern's group, actually, it's single atoms that they live in the cavity. And so this is really sort of, I would say, an exciting new frontier. And so the setup that we use is one where we have an array of clouds of atoms. We can have sort of up to 20 sites in this array. Some of the work I'll talk about is fewer, but up to about 20 sites in the experiments that we've done. Just to give sort of a sense of the parameters, we operate in a regime that is in what's called the strong coupling regime for single atoms, in the sense that if you look at the G, the vacuum-Rabi splitting, squared over the characteristic decay rates, that ratio, the cooperativity, is larger than 1. But it's not much larger than 1. And so we actually, it turns out that for the physics we're looking at, we do benefit from having a collective enhancement, from having actually order 1,000 atoms per site of this array. And so the physics that we do benefits from actually this, the cooperative enhancement of interactions. To generate interactions, we have some drive field that actually drives, so the full story is we can turn on the interactions with this drive field. So that process where you flip a spin and put a photon in the cavity is a Raman process. That process is not resonant, but the pairwise process where you where you have the spin exchange mediated by the cavity, that will be resonant. Okay, so we have this drive laser that turns on interactions, and then the other ingredient is that we have the ability also to do any sort of local rotation we want by optical addressing with a focused laser beam. Okay, so in the cartoon picture, just to add one more wrinkle, in the cartoon picture I treated the atoms as spin half. Our atoms actually have a spin 1 ground state. And often the way that we like to probe this system is we start with all the atoms in the n=0 state, and we turn on this control laser that then generates this process where in the spin 1 system we can now generate +1, -1 pairs mediated by photons in the cavity. So that's what that would look like for 2 atoms. This looks actually a lot like a process that has kind of a long history of being studied in, for example, Bose-Einstein condensates, where one has direct collisions give rise to correlated atom pairs in the +and -1 state. So this is kind of a spin mixing process. It's been used to make entangled states, like twin Fock states and a class of squeeze states. In our system, the main difference is that actually this is happening on kind of the millimeter length scale over which our cavity mode is focused. So atoms can be a millimeter apart, and they can still participate in this spin mixing process. This is kind of an illustration of one of the early experiments where we saw this, which was actually done by Emily Davis, who I think is sitting here in the audience, where we essentially had, actually this is maybe after your time, but she was the first to see this happen in the cavity, and now we did this in this array of atom clouds where each pixel is basically the population in one of these 3 internal states. In a particular array site, the different rows are different iterations of the experiment. And you can kind of see when there's more atoms in the -1 state, there's also more atoms in the +1 state, which seems to kind of match that picture I gave you of this correlated pair creation. This isn't, of course, yet enough to say that there's entanglement. It looks like it's kind of doing the right thing. But one thing we wanted to ask is actually, can we really see that there's entanglement being generated in the system? And a way that you can do that is to look at squeezing of quantum fluctuations. So in this simplest case, this is an experiment where physically we have 4 atom clouds, but for now, they're actually just collectively interacting via the cavity. The spatial position doesn't matter yet. The Hamiltonian for the system, because these are spin 1 atoms, I can write it down in terms of not only some collective spin, that's the sum of the spins of all the atoms, but also some collective quadrupole moments. So for example, this operator that I called QZZ represents the population difference between the + and -1 state versus the 0 state, right? So it's quadruple in this direction. So this is a quadratic Zeeman shift. This is the cavity-mediated interaction. And one can kind of visualize the dynamics this generates on a generalized block sphere, where in this case I've shown Fx as one axis, this QZZ, this population difference between the side nodes in the 0 state, as another axis, and then here's another quadruple operator that makes the dynamics that one gets is that this fx squared term essentially gives rise to an fx-dependent precession rate about x, which twists the initial kind of coherent state into something that's squeezed. And the main point, actually, you're not going to have to worry about these weird variables that are labeling the axes on the sphere. The main point is we start with some Gaussian fluctuations, and the first thing the interactions do is to squeeze them, and we can essentially measure in any basis in order to detect that sort of, as you rotate this state and let's say measure the fluctuations along x, one can see the noise dip below the standard quantum limit, which is the smallest it can be without entanglement. And so that gives us a way of seeing, okay, so at least we were able to sort of, in this, through these collective interactions, generate entanglement in the system. Now, I said we wanted to actually take advantage of the fact that we have local detection. And so a first question we can ask is, if I do that experiment, but now I look at just one subsystem, the left half A or the right half B, do I still see entanglement? And perhaps not too surprisingly, if I just look at one subsystem and I try to look for squeezing, the squeezing is degraded, and that's because I've thrown away information that was in the correlations between the two subsystems. So that makes sense. One kind of neat thing is actually if you wanted to have entanglement locally, you could actually undo the correlations between the two subsystems. So the way we can do this, we do this global squeezing operation. Then we can do a local pi rotation of the spins on subsystem B, and then do a second global squeezing operation. And what that does is it basically enhances the interactions in the individual subsystems, but cancels the interactions between them. And so now actually we do have, two independently squeezed states in the left and the right half. So that starts to kind of show these ingredients of the local detection and the local control. Just as a brief aside, you might say if you just want local squeezing, why do you even bother with these weird non-local interactions? And in fact, a different thing we've been working on in another setup in our lab is using local Rydberg interactions to generate squeeze states. So that's a story for another day. I just thought I'd advertise that. But the cool thing about the cavity is that in principle we can have a lot of programmability over the structure of entanglement. So we can generate global entanglement, as I showed you. For some applications, like in quantum sensing, maybe you want to actually also use local rotations to control the squeezing, give you sensitivity to local or a global field or a gradient in a field, or does one have spatial resolution through these independent entangled ensembles. But what I want to get to is also asking, can we start to have sort of even more structure? Like, can you give me a graph that says I would like to have this particular structure of entanglement between my nodes, and is there a way for me to use the cavity to generate those richer structures of entanglement? And so really kind of as a way of even exploring what the power is of this cavity for kind of richer quantum control, we basically set ourselves this task: can we make these so-called graph states, which are resources for computation, as I indicated earlier, for example, preparing topological states by measurement, and also in, for example, quantum sensing. So what exactly do I mean by a graph state? So if you have heard of these states, they're also called cluster states, you might have been more likely to hear about them in the setting where each node is a qubit. And in that case, basically the idea is the graph specifies the structure of correlation between the nodes. So if these were qubits, it turns out the way you would make such a state is you could start with each qubit initialized along the x direction and apply a Hamiltonian that's basically the nearest neighbor Ising interaction, or equivalently a CZ gate, sort of on each edge of the graph. And that would make a state where essentially like sigma x on this red site would be correlated with sigma z on the sites that are connected to it in the graph. So that's the discrete variable version of these graph states. Because we're working with many atoms per site, our system is better approximated with each site being sort of like an oscillator that I could talk about the two. There's some Gaussian state. I could call these two quadratures x and p just to simplify things. And in that case, the way that these graph states are defined is, well, one is sort of the operational definition of how do you make it, and it would be you start with each of these sort of effective oscillators in the vacuum state, and you turn on a Hamiltonian, which just looks like xi xj instead of sigma zi sigma zj. And what that does is it generates correlations between p on a given site and x on the sites that are connected to it in the graph. So another way to kind of, so the issue is we don't really have arbitrary control over these aij, couplings. What we have are some collective interactions mediated by the cavity. So is there a way to use those global interactions to access some graph that I choose, or that you give me? So the neat thing we realized is, okay, so another way to kind of phrase the definition of these graph states is I have some adjacency matrix that specifies the edges in the graph. What I would like ideally is that the sort of vector of the p's on all the sites minus this matrix times the vector of x's goes to 0, or a squeeze difference. Okay, yeah?
Can you make certain pairs interact stronger by having them be tuned in exactly the right way?
Yeah, so you could play tricks with like local start shifts or like moving things in and out of the cavity to control the strength of coupling of different nodes to the graph. And actually that could be a valuable tool.
So then you could, in principle, individually control the same.
And so in principle, you could say, like, I'm going to move things in and out of the graph in the cavity in pairs, and, you know, but that's not going to be the most efficient way to do it. Local start shifts could help. Yeah, so let me tell you sort of what the general recipe is, and I think you'll kind of see where that would come in.
Monika,
Yeah.
I also have a question.
Yeah.
It's a theory question,
Yeah.
but I'm blanking on, like, what is the status of, do we have a measurement-based kind of analog for this kind of big spin or continuous variable?
What do you mean by as a measurement? Oh, does measurement-based quantum computing
Yeah,
exist?
something like that.
Yeah, so people,
cluster,
right, so there
how
are
they
lots
are
of people who think about it in the context of photonics, right, where you really have, so where your oscillators are just photon modes. And they're essentially for computation, you need to be able to not only make these Gaussian graph states, but also have some kind of a non-Gaussian operation, which could actually be a measurement. So in photonics, it could be a photon detector. Here it could be atom counting, exactly. So there's one other ingredient you need, and in fact, actually in these cavity QED settings, people have made non-Gaussian states, and so you could imagine combining those. Yeah. Good. So basically the structure of entanglement for any of these states, it's just specified by this adjacency matrix. And so one thing we can do is we can diagonalize that matrix. I can diagonalize this matrix, and I can get a set of eigenvectors, which essentially tell me what are the collective modes that I should squeeze, and a set of eigenvalues, which are going to tell me what are the orientations of the squeezed quadratures. So in this simple example, if I have two modes, this is actually an EPR type entangled state. If I diagonalize this, the eigenmodes are just the symmetric and the anti-symmetric mode of these subsystems. And the eigenvalues are plus or minus 1, and it turns out that's going to tell me that these squeezed quadratures should be oriented 90 degrees from each other. So this is a prescription for making this state. And that's something we can do. So if we want to do this, we first do our global squeezing operation that squeezes, let's say, the symmetric mode. Then I can do a local pi rotation that essentially converts the anti-symmetric mode to the symmetric one that will now couple to the cavity. I can also do a phase space rotation to kind of choose which is the squeezed quadrature, and then I do one other global squeezing operation. And now I have this scenario of the symmetric and anti-symmetric modes being squeezed 90 degrees out of phase. And that works. So this is, in this collective mode basis, a way of characterizing this EPR type entangled state between two modes. And one way one can really sort of show that there's actually entanglement between the two spatial modes is one can write down a witness for entanglement, which is essentially the product of uncertainties in these two orthogonal quadratures. And if that's less than 1, that tells us there's entanglement. To give you a feeling for why that actually tells us there's entanglement, you can think of it as essentially you're asking, is it possible to use one subsystem to predict two non-commuting observables in the other subsystem to better than the standard quantum limit? And it turns out that actually generically quantum mechanics lets you do that. That's one of the cool things about quantum mechanics. And it's possible because the sum of the x's and the difference of the p's between the modes actually commute. And so that means if I kind of use system B as a reference, then I can sort of detect changes in system A in either x or p to better. There's no Heisenberg uncertainty principle to how well I can detect those changes. So for separable states, we would have an uncertainty relation here, but entangled states can violate that. That's actually been thought of as a resource one could use, for example, to simultaneously sense two quantities that don't commute, or perturbations in two quantities that don't commute. But for us, one thing it's useful for is just saying this allows us to witness entanglement between the two subsystems. And one can even satisfy a stronger criterion known as EPR steering that actually says that it's a resource for quantum teleportation. And that actually is sort of a necessary ingredient for protocols that use these graph states for computation or for measurement-based state preparation. Okay, so one can go further. The furthest we've gone for really sort of provably generating entanglement in the system is a 4-mode graph state. So we ask, when you make this square graph state, this is the correlation matrix you would want. Again, we diagonalize it. It turns out, in this case, the normal modes are fairly simple in the sense that we can access them, again, just by these local pi rotations of the spins. And so by doing a sequence of squeezing operations on these collective modes, we can make the state that from these kind of squeezing curves, we can essentially reconstruct a correlation matrix that matches quite well what we set out to generate, which is this square graph of correlations. And you can also directly do kind of independent rotations on the different sites to measure what is the correlation between P on this site and the X's on the neighboring sites. So we can measure these so-called nullifiers, which ideally go to 0. In practice, there's finite squeezing in the system. But if all of these nullifiers that measure the correlations at each vertex are sufficiently small, then you can really prove there's no way to cut the graph into a product of subsystems, and that's in fact satisfied in this system. So that illustrates, we've done it with 4 modes, but it's a very general scheme in principle where you give me a graph, I diagonalize that matrix, and I have a recipe for preparing that state just by global interactions plus local rotations. So that's pretty cool, and we can dream about things one might want to do about it. And I think the nice thing is, again, that we have this non-local connectivity. Is there a question? Yeah.
So,
yeah.
Do these states remain Gaussian all the time, or no?
So for our parameter regime, the states remain Gaussian. So we're kind of really like these pair creation dynamics are really just generating a few pairs that generate squeezing by a factor of 2 or so in the experiments we've done. And so if you want to make it non-Gaussian, there's sort of 2 directions you can go. One is if you have sort of a small enough number of particles and coherent enough interactions, then just these dynamics will start to give you non-Gaussian states. Or you could add in an ingredient like measurement, right? So atom counting is a way to access non-Gaussian states, and so like squeezing plus measurement could be a neat way to go. Yeah.
Maybe I would expect that if you would use the tuning to your cavity and atomic transitions, that will, so that you get more entanglement between cavity mode and spins, you also get non-Gaussian too. Like now it's Gaussian because you eliminate the cavity mode so that it's all just oscillated.
So there might be interesting things that happen, if you actually are sort of like really including the full sort of model, or like including the photons. I'm afraid of that because it quite quickly gets complicated. I think it's chaotic actually, even, but once one starts to include the photons. But yeah, exactly. And so for this quantum control direction, in order to even start characterizing what are the entangled states we're making, it's nice to start simple. I agree that one can definitely make it more complicated, and I think there's a fundamental question about sort of there's some dissipation. On the other hand, we're in this regime of certainly strong collective coupling, lets you access strongly squeezed states in principle. So it could be much stronger squeezing than what we've shown here. To access non-Gaussian states, at least for some of the more exotic states, you want like Schrodinger cat-like states. You actually do need strong single atom cooperativity, and there is a sort of borderline. But I would say probably we're in a regime where some non-Gaussianity through the dynamics should be accessible, but we haven't explored it yet, and it would get easier at stronger atom photon coupling. If that makes sense? Yeah. And yeah, if you include the light field, then the question is just now I have some entangled state of the atoms in the light, and so, right.
Entangled.
And then you want to maybe.
Resonance.
Sorry.
To be really entangled, they probably need to be near resonant.
For the atoms in the light to be entangled. But that's not a necessary condition to make it non-Gaussian, right?
If the cooperativity is large, yes, single atom cooperativity. Otherwise, it will be just like something.
So I would say, sort of going near resonance for the cavity is definitely not a necessary condition to access non-Gaussian states, right? Just this effective spin model can get you there. But I agree there could be interesting many-body physics, including the light field, if you have ideas of what exactly should be looked at love to talk about it. So yeah, great. Okay, so okay, so now you can dream if you scale this up and have sufficiently coherent interactions. What can you do with this ability to have the arbitrary non-local graphs? I just thought I would kind of say what are the directions this could go. So there's a number of in this context of sort of preparing states by measurement. There's a number of error-correcting codes, for example, where it would be great to realize them, but the sort of initial graph state that you would need is not something that's easy to make in a just two-dimensional system with local interactions. So just for folks who think about these things, I threw up a few examples of like low-density parity check codes where one has some non-local couplings that can improve actually the overhead and the threshold of error-correcting codes. Hyperbolic codes, which live on some in this weird hyperbolic geometry. You can't naturally do this with local interactions in 2D, but maybe with non-local interactions you can measure these, in this case, 12-body stabilizer operators, or this so-called Haas code, which is a model for a self-correcting quantum memory. So this involves, again, some 8-body operators. It's a funny geometry that looks hard to realize if you think about sort of atoms in a lattice, but you could say, what is the graph state I need? You diagonalize the matrix. My student actually used to see what this would be like, diagonalized the matrix and said, okay, this is what the collective modes would look like. Here are the eigenvalues that give you a prescription for the sequence of operations that prepares the state. These things are certainly most well thought about in the case of discrete variable graph states, and so there you definitely need to go to stronger atom-photon coupling if you want to explore this, and I'll sort of touch on an experimental direction for that in the end. But also, I think an interesting question, and if anyone has thoughts on this, I'm curious, is are there sort of continuous variable analogs of these things that we could explore in our current platform just by scaling up to more modes? Yeah?
I'm a little bit curious. So in this protocol, the entanglement lives on the Siemens sublevels. What is the coherence time that you can achieve there?
Oh, so it turns out that because the physics is generating these pairs in the +1 and -1 state, the pairs actually are, to lowest order, insensitive. The energy of a pair is insensitive to a magnetic field. And so it's actually more robust than you might think, as long as we're focusing on kind of this, what I call this spin-domatic squeezing. So as long as that's what we're focused on. More generally, it's the noise, magnetic field noise is on the milligauss level, so it's sort of kilohertz type coherence if you're dealing with something that's magnetic field sensitive. But that's why we'd like to actually work in this regime where we're magnetic field sensitive. Another way to say that is that Hamiltonian commutes with like a field along Z. So yeah, that's kind of nice. Okay, we've been thinking actually about intentionally converting to something magnetic field sensitive to use these in some sensing applications, but otherwise it's kind of protected. Okay, so you might ask, how does this scale? It would be nice to go to more than 4 modes. And in principle, in fact, the method generalizes to where you give me a matrix that specifies some M mode graph, and there's some sequence of M collective operations that will make that. And that's maybe not totally obvious. You might think you need M squared operations for this arbitrary connectivity, but actually these M collective operations suffice. So that's kind of neat. And also, the rate of each of those operations is collectively enhanced, right? So if I fix the number of atoms per site and I scale up my array, the actual total time it takes to make the state, if you're limited by the cavity-mediated interaction, is fixed. So that's also kind of nice. If you want to make the most general graphs, those eigenmodes might have some weighted couplings. This comes back to Eugene's point about maybe I should shift the local sort of strength of coupling to the cavity, and that's something one could in principle do. If the graph is translation invariant, then there's actually sort of a nice situation that the eigenmodes are actually just spin wave modes. So that's kind of cool, because that means that if you want to basically sequentially couple different eigenmodes to the cavity, what you can do is just apply a magnetic field gradient, and that will transform between different eigenmodes. And so this actually, we realize this is a nice picture for thinking about actually some previous work that we've done, where we essentially think of this as, if I want to sort of, one way to say it is if I want to kind of Floquet engineer a particular Hamiltonian in my cavity, one way I can do it is essentially have a time-dependent drive field So I'm going to essentially pulse this field on at different times that correspond to the times when different spin waves are coupled to the cavity. And the intensity of the field at each time essentially sets the dispersion relation at some particular momentum, at some spin wave momentum. And so that's pretty cool because just by pulse shaping of my drive field, I can basically make any dispersion relation I want for the spin excitations. That's the momentum space picture. The real space picture is if I want to control these spin exchange couplings as a function of distance, it's basically each spectral component of my drive field modulation maps to the spin exchange coupling at a particular distance. Yeah?
So you want to modulate, so I didn't understand the protocol, so you have gradient which you change in time.
So the gradient, this is actually just a fixed gradient, and you can think of the gradient as basically converting different, what starts at k equals 0 is essentially driving block oscillations for the spin excitations, kind of, right? So the gradient gives you a way of cycling through which spin wave couples to the cavity over time, right? So what was at some non-zero k at a later time is at k equals 0 and couples to the cavity. Yeah? 8 more minutes? Okay, great. So this is neat because, yeah, it lets me kind of sculpt my dispersion relation, or equivalently, the spectrum of the drive field should dictate the couplings as a function of distance. Here's a simple case where we apply this magnetic field gradient, and we have just a monochromatic drive field. And in this case, if I now look at essentially correlations between the, let's say, atoms in the plus that got generated in the +1 state on site I, and atoms in the -1 state on site J, you'll see that these correlations are strong on the diagonal, which indicates these pairs are forming locally, and not anymore at long distance. So we've gone from this kind of long-range or global cavity-mediated interaction to a local one. But now we can also, take this a step further, have two frequencies present in my control field, and now I'll also turn on interactions at some fixed distance that's set by the frequency spacing between those two teeth of my drive field. And so that, of course, generalizes. I can now scan the frequency, vary the frequency at which I'm modulating my drive field, and as a result, the distance at which interactions are on and the resulting distance at which I see correlations will track. I've shown actually two cases here. The one on the right is the one where I pulse the drive field on at discrete times that correspond to the times when different spin wave modes are coupled to the cavity. And that actually very cleanly generates interactions not only at the distance corresponding to this overall modulation frequency, but also at the length of the chain minus the distance. It's because I've essentially precisely engineered the dispersion relation for the finite size system with periodic boundary conditions. So that's kind of cute. You can generate periodic boundary conditions. It turns out if you don't pulse, but you use the analogous continuous waveform, that gives you the same system with open boundary conditions. So you can go, for example, from an open chain with nearest neighbor couplings to a ring. So this starts to illustrate also that kind of you can make a geometry of this interaction graph that is different from the physical geometry of my atom cloud, of my 1D array of atom clouds. And one kind of fun thing that you can do is actually ask, I program in some graph, I measure some correlations, and can I actually just in a black box way from the correlations reconstruct what's the graph that I had programmed in? So here's a simple example where we turned on just interactions at distances of 3 sites with open boundary conditions. We measure some stripy correlations here, which kind of maybe match what you might expect. And you can actually now sort of do a reconstruction procedure where I take some unsatisfied correlations, decay as a function of distance, and ask what's sort of the best fit embedding of these 15 sites into, in our case, we just picked 3 dimensions, so that sites that are strongly correlated are near each other. And then we also color the bonds in a way that the bond color is actually the inferred coupling between the sites, which you can actually back out by inverting this correlation matrix. And the opacity is the strength of the coupling, and actually what pops out, so all possible bonds are drawn, but what pops out is precisely these 3 chains that I can kind of think of as, the sites whose positions are 0, 1, or 2, mod 3 are connected in chains. Okay, so that, and again, that just comes from the measured spin correlations and kind of verifies the graph that we set out to make. Now we can be a little fancier and say, let's have some chain with nearest neighbor interactions. We'll add in periodic boundary conditions, and then we'll also add some rungs across the chain. Looks kind of almost like a wheel. And just for fun, we can also control the signs of the interactions. So it turns out if I introduce a pi phase into the modulation, that actually takes me from ferromagnetic to antiferromagnetic interactions. And so, we can reconstruct the correlations that come out of this. And if you look at the geometry that this generates by this, this reconstruction, it turns out this is actually a Mobius strip. Why is the Mobius strip? Well, basically the single edge of the strip is this red circle here, and then these kind of spokes of the wheel are the rungs of the Mobius strip, right? Yeah?
How do you generate the phase? Can the coupling be complex, actually?
Yeah, exactly. So it could be complex. For whatever reason, we haven't gotten around to playing with it, but we should play with it. It could be complex, yeah. But it's really just, again, you just have different, you add up these, you add up these sinusoidal modulations at different frequencies to get your waveform. But now if I put a pi phase or some other phase into one frequency component, that changes the phase of the coupling, that distance, right? So basically each distance where I want interactions corresponds to a frequency component of my modulation, but I also have control of the phase. Yeah, exactly. And so in principle, this is quite powerful, and we should explore it more. Here's sort of a gallery of some of the things that we did so far. You make a ring. You can make a sort of ladder geometry. This is triangular ladder. I showed you the Mobius strip, but you could also do a cylinder without the twist, right? And so this is pretty versatile. And I want to emphasize this is just with sort of a regularly spaced array. You can even kind of break translation invariance if you change the spacing of the array, or also if you use not just a physical magnetic field gradient, but an optically imprinted gradient. There's even more flexibility. Okay, so a few of the directions that we've explored, I already talked about spatially structured entanglement. We've explored sort of structures of correlations that you can't simply visualize by sort of plotting the nodes in 3 dimensions, but things like structures where the best way to think about the correlations is having some emergent extra dimension that looks like a tree graph. It's kind of a toy model for quantum gravity and geometry emerging from quantum correlations. And we've also thought a little bit about, can you use these programmable interactions to kind of study optimization problems that map to kind of energy minimization in a frustrated magnet. Just to say a little bit about that, I showed you these these reconstructed graphs where the bonds said something about the sign of the correlation. And naively, it's actually maybe not obvious that this sudden quench where I turn on interactions will actually generate, that ferromagnetic interactions will generate ferromagnetic correlations. That might not be obvious, right? It's just a sudden quench. The reason that this actually happens is that, remember, we have not only these spin-spin interactions, but also there was that quadratic Zeeman shift in the spin-1 system, which means there's an energy cost in terms of the internal state energy to generating these atom pairs. So that actually means that the system can lower its interaction energy by sort of dumping energy into this quadratic Zeeman shift. And so that's my intuitive picture for why, when we just suddenly turn on these interactions, for example, making like this anti-ferromagnetic ladder, why the spin texture sort of looks like a low temperature state of this anti-ferromagnetic XY model. Yeah.
So one question I said, you guys are trying to infer basically the Hamiltonian.
So far, this is kind of a way of checking that we've programmed in the couplings we thought we should. At some level, that's so far what we've been doing. Does that make sense?
Right. You're doing this only from these spin.
Yes. Yeah. And so it turns out that, at least for sort of the early time dynamics, what one expects is in fact that the spin correlations do actually give a measure of the inferred coupling. You can kind of think of it as, sorry? Yeah, so one way to think about it is, at the end of the day, we take the correlation matrix and we invert it, and the inverse correlation matrix is the inferred coupling. And the way to think about it is it basically comes about from asking, you're essentially trying to figure out of the sort of fluctuations on a given site, how much of that is explained by each other site, and and what's the correlation between them. And it turns out that the thing that gives you the inferred coupling is the inverse coupling.
And you can back out if they're coupled, perhaps not the magnitude.
The overall magnitude, there's some overall scale factor that maybe you could ask about, but yeah, you can also back up the relative magnitudes. you know, it might not immediately be obvious because you say, well, the correlations spread, right? So why is it that if the correlations have spread, I won't like think that there's a coupling between these distance sites that aren't actually coupled? Turns out this trick of taking the inverse correlation matrix already accounts for the fact that if there's some like variance on a distance site that's explained by the correlations having spread, that gets taken out. So, yeah, okay.
It's time that we summarize.
Okay,
It's already 40
okay,
minutes, so.
but I spent some time on questions, so
That's already
I'm getting
included.
very close to this.
Okay.
Okay, so I just wanted to say, where was I going with this? So somehow the dynamics naturally generate things that kind of look like a low temperature state of the classical XY model on this graph, so that's kind of interesting. One also could do kind of slow quenches where one is more adiabatically kind of starting with a situation where the ground state is all atoms at 0 and preparing a low temperature state of the quantum spin model that we have. I'll maybe skip over this. But yeah, okay. And so, you know, one setting to do that in might be actually to engineer some topological band structure. Mohammed asked, can you control the phases of the couplings? And indeed, that's something we, in principle, have control over. You can decide, do I have open boundary conditions, closed, twisted boundary conditions? There is also an on-site interaction that we have some tunability of. And so all of these things, I think, mean we really ought to start playing with some topological physics. One thing we've been thinking about is, can we make, like here's sort of a minimal model for having perfectly flat bands that could be a fun thing to play with, combined with some tunability for on-site interaction. To get into sort of a really strongly interacting regime, you need to get to stronger atom-photon coupling, so that you could have, let's say, a hardcore boson model with a single spin on each site. And one direction that we're pursuing is actually building not an optical cavity, but a superconducting millimeter wave cavity where the dream, so we've started to test one of these cavities. We don't have atoms trapped in it yet. But the dream is that you could really have like a large 2D array in a pancake of this cavity, maybe even another 2D array that it talks to in another pancake. And so again, our single atom cooperativity is 5. I think, you know, in the optical domain, if we put in better mirrors, we can get that to be order 100. But the idea with this millimeter wave cavity is that this figure of merit can be like 10 to the 8. And so there's sort of just orders of magnitude to push in terms of the coherence of the interactions, and that would be really exciting for going to really single atom qubits and arrays of single atom qubits. So with that, I'll just kind of summarize again the toolbox. We have programmable interactions and programmable entanglement, and here are some of the prospects I can
One last question while Angel tries also to set up, since we're over time.
So this triangular ladder,
Yes.
you said it's a classical model, so
It's not. Well, sorry, go ahead.
So you engineered like ZZ interaction between your neighbors, so what exactly?
So I didn't want to say it was a classical model. It's, you know, we have a full quantum XY model. But one thing that, even if you just do the simplest thing of this suddenly quenching on interactions and you ask what do the spin correlations look like, it looks, it's an XY model. With, in our case, we programmed it in so it's just these triangular.
It's really
just
triangular.
we could add longer range couplings if we wanted, but that's what we have. And it's just that the quantum dynamics, if you ask sort of what do the spin correlations look like, it looks like a low temperature state of a classical XY model if you just do this simple quench, which is kind of surprising because, again, it's just a quench, right?
Nice.
Yeah.
Thank you.
Yeah, that's something that we sort of started to explore. Yeah.
So let's thank Monika for the great talk.